Okay, I'm going to talk about polarity. So, when we're talking about polarity, we could be talking about polar bonds or polar molecules. Um, and so sometimes both are true for a compound, sometimes not. So we're going to start with the simpler case of polar bonds. And polar bonds are just bonds that have some center of positive charge and some center of negative charge, meaning the two atoms that are involved in the bond, one of them is partially positive and one of them is partially negative. So it's not really full charges. It's partial charges because they're still sharing electrons, okay? Because we're focused on covalent compounds, not ionic. So an ionic compound, you actually have electrons given from one thing to another. So you really have something that's positive, something that's negative, and they're really two separate things. So you don't talk about polarity with respect to those. Uh, but for covalent bonds, you can actually have polar bonds or non-polar ones. And the polar ones have some separation of charge. So you have a little bit of charge on either side of the bond. Um, and really what this is due to is when you have some significant difference in electronegativity between the atoms that are involved in the bond. So for instance, if you had, two atoms of the same element bonded together, those have the exact same electronegativity. So that would be nonpolar. But if you have something that has a low electronegativity attached to something that has a high electronegativity, as long as they're not too big of a difference, it will create a polar bond. If it's a very large difference, something greater than about 2 of a difference in electronegativity, then it actually ends up being an ionic bond. The electrons completely transfer. But again, we're not dealing with that right now. Um, and so it really is based on differences in electronegativity. Now, you don't always have to look up electronegativities. In general, if you have different elements, atoms of different elements bonded together, we generally just call it a polar bond. It may only be very slightly polar if those electronegativities are very similar. Um, but in general, if it's the same element, it's nonpolar for sure. If it's different elements, we just call it a polar bond typically. Um, Now, when we have those charge centers, okay, so the atom that is positive or partially positive and the atom that's partially negative, we will actually label those. Or sometimes, if we're trying to stress that this is a polar bond, and we want to talk about kind of how it's interacting with other molecules, then we may label it with a delta plus and a delta minus. And so the delta indicates that it's just a partial charge. So it's not a 1 plus, it's not a 2 plus, nothing like that. It's a partial charge on one end of the bond and a partial negative on the other end. And so if we had, say, an HF molecule, so hydrogen attached to fluorine, then we could put the delta plus over by the hydrogen because your hydrogen is less electronegative than the fluorine, and we put a delta minus by the fluorine. Okay. And so if you had drawn just the Lewis structure instead of having kind of this diagram, then we'd just have H single bonded to F, and you'd have lone pairs on your fluorine. And so then we could label and put a delta plus next to the H and a delta minus next to the fluorine, just to stress that that is a polar bond and where the partial positive and negative is. But on that diagram that I've got down there, you can see another notation on it. There's actually an arrow shown there pointing towards the fluorine. And that's just another way to indicate the same information. When you draw an arrow through that bond or possibly next to it, you always point it towards the negative end of the bond. And so I could also just draw it next to this Lewis structure, draw an arrow. And usually we would put kind of a cross at the end of it, so a little plus sign essentially at the end of that, so you know the other end's the positive side. And that, when we draw those arrows, usually we call that a dipole moment, okay? And something with a dipole moment is polar. Um, and so if you just have two atoms bonded together, then if that bond is polar, then that is a polar molecule. But when we start, putting together more than two atoms, now we have multiple bonds. And each of those bonds could be polar or nonpolar. And then they each contribute overall to the entire molecule's polarity. And so then you would have to understand, do the individual bond dipoles, do they cancel out, or is there something remaining? Um, and that'll determine whether or not the overall molecule is polar. So let's talk about kind of the different scenarios we can have with, polar bonds and polar molecules, or, non-polar of those things. So if we had a molecule and it only contained non-polar bonds, most often that's going to be a non-polar molecule, okay? Because if you think about it, if you don't have any bond dipoles, how in the world would you have an overall dipole in the molecule? Well, it can happen. The only time it happens is if you have some lone pair that's causing asymmetry in the molecule. And so if you have a lone pair kind of off to one side in the molecule, then you really have this cluster of negative on one side. And so then the other side with the atoms is going to, by default, be partially positive. And so that's the only case where you'd have all nonpolar bonds but polar molecule. Now, when you have at least one polar bond, then it may or may not be polar. Okay, so it's going to be non-polar if those polar bonds are completely symmetric, and so if all of those bond dipoles can cancel out, meaning they'd all need to be kind of oriented opposite of one another. And so that can happen, but you can also have where you have polar bonds and overall molecule is polar. Okay. And that's going to be if there's asymmetry in it. Okay. So if you have a polar bond, on one end, and then completely opposite, you don't have one that can cancel that out, then it's going to overall be polar. Okay, so you can kind of focus on it as a little bit of a symmetry thing. If you have kind of something that is just by itself and doesn't match up with something else in the molecule, it definitely isn't going to cancel out and be nonpolar. Okay, so let's look at a couple of examples where I've got some diagrams of the molecules, and then we'll just look at Lewis structures and try to figure some of these out. So here I've got a structure of a water molecule. So we've got our H2O molecule. And H2O, if you draw the Lewis structure, then you have an oxygen and it is single bonded to two hydrogens, and then there's two lone pairs on that oxygen. Okay, and so really that's a tetrahedral structure, right? That is the parent geometry or electron geometry. But since there's two lone pairs, and those are what we're not focused on when we're talking about the shape of this is bent. Okay, and so that's why in this diagram they've got those hydrogens at an angle instead of straight across. Okay, so you might draw the Lewis structure as if they're straight across. That doesn't mean three-dimensionally, that's what it is. Okay, so you use Vesper theory to predict that. And so Vesper theory tells us it's bent and that there's this less than 109.5 degree angle there. And then if you think about the individual bonds, oxygen and hydrogen do have significantly different electronegativities. Oxygen's is quite a bit higher. And so what happens is the oxygen pulls more of those shared electrons towards it. And so you have a bond dipole pointing towards the oxygen for each of those bonds. And so that's what those black arrows there are. Those are the individual bond dipoles. But then if you want to think about overall what's going on with that molecule, you would have to put that information all together. So really you're doing a vector sum, which you may or may not be familiar with, but basically I'd break that down into the components that make it up, and then see if anything cancels out and if anything adds. And basically what happens is this one pointed in and this one pointed in, those essentially cancel each other out. But then you have the ones pointing up, and those two pointing up, those actually add. And so that's where this molecular dipole comes from, that's pointed towards the oxygen. And so towards the oxygen, we have a net dipole for the molecule. And so since it has a net dipole, that actually is a polar molecule. So it does have a partially negative end, the oxygen end, and a partially positive end, the hydrogen end of the molecule. Whereas this next one I've got CO2. Well, if you were to draw the Lewis structure of CO2, you would have carbon double bonded to two different oxygens, and then those oxygens have lone pairs, but the central carbon doesn't have any lone pairs. It's just got two double bonds, meaning it's got two electron groups, meaning it is a linear structure. And since it has no lone pairs, it's linear in shape. Okay, so that's why this one, I actually have the carbon and then the two oxygens coming off at 180-degree angle. And so for that one, those bonds are also polar. So carbon and oxygen have significantly different electronegativities. Oxygen's is higher, so there's bond dipole pointing towards the oxygen on each side. Okay, but those are pointing completely opposite of one another, so they definitely cancel out, and there's no net dipole for the molecule. And since there's no net dipole, that means that overall that is a nonpolar molecule. Okay, so there's two examples there where you've got molecules that have polar bonds, but one of them overall is polar and the other one is not. Okay, so for, figuring out whether or not something's polar or not, a big part of it is, do you know how to figure out the three-dimensional shape? Because when you draw things on paper and just try to figure out what cancels out, sometimes you can mislead yourself. For instance, the water molecule, if you drew those hydrogens straight across, you might think, well, that's completely symmetric, so it cancels out. Well, it's not really. Not three-dimensionally, it isn't. Okay, so let's see. I've got a couple more little notes before we go through some more examples. And so I wanted to talk about the individual shapes and how they tie to polarity, because we're focused just on octet structures, and it can be simpler than when you have the exceptions. When you have the exceptions, it starts getting a little more complicated. But for octet structures, let's say we have a linear molecular shape. Really, the only way that it is polar is if the atoms on the ends are different. If the atoms on the ends are the same, then their dipoles are going to be the exact same magnitude. It's going to cancel out. But if you say have a chlorine on one side but an oxygen on the other, then the pull oxygen has on those electrons versus what chlorine has is not going to be the same, so it would end up being polar. Okay, but in this case with the BeCl2, that one would be nonpolar. Okay, but if I swapped out one of those chlorines for something else, it would end up being polar. So you got to pay attention. Are my outer atoms the same thing or not? Okay. Similar if you had a trigonal planar structure. Okay, if we have BF3, all of those fluorines have the same pull on the electrons, and so that overall, the pull they have on it would cancel out, and so it would be nonpolar. But if I swapped out any of those fluorine atoms for something else, so if at least one of those is something different, it would be polar. Okay, now another way you could be thinking about this, which actually when you're getting started can be kind of helpful, if you think of it like a tug of war, and that central atom is kind of hanging on to things, and then you have the things on the outside pulling, and the question is, do you move that center atom one way or another? And if so, if something has a stronger pull and can kind of pull it towards it, then it's a polar molecule. But if they all are equal strength, then that central atom is just going to stay put and it would be nonpolar. Okay. So sometimes that can help. Okay, so this is two of our molecular shapes, linear and trigonal planar. So if it's all the same on the outside, it's nonpolar. If any of those atoms on the outside are something different, then it's polar. Now, with the trigonal planar structure, you can also have the scenario where it's a bent structure, and that comes up when there's a lone pair on there. And so in that case, you have a lone pair off to the side and then atoms on the other side, and that's always going to be polar because you just have this region of negative stuff. So it definitely is negative on that end. So it's definitely polar overall. Okay. Now you can get a polar or this bent structure also from a tetrahedral parent geometry, just when it has two lone pairs. And the same would be true. It's always polar. So that's an easy one. If you figure out that the molecular shape of something is bent, you know 100% it has to be polar. Okay. Um, Now, another one of our molecular shapes is tetrahedral. If we have a tetrahedral structure, it's similar to when you have the linear and the trigonal planar. If everything attached in that tetrahedral structure is the same atom, then it's nonpolar. But once at least one of those has changed to some other atom, it's polar. Okay, it doesn't matter if you change one of them out, two of them out, or three of them out. If at least one of them is different than the other outer atoms, then it's polar. Okay, and then the last molecular shape that we deal with is, oh, I'm sorry, with octet structures is trigonal pyramidal. And when you have a trigonal pyramidal structure, similar to when you have a bent structure, there's always a lone pair off to the side, okay? And so you always have kind of this region of negative charge on one side of the molecule. And so that's always going to be polar, no matter what it's made up of, okay? So that's kind of your two you should definitely know. Bent structures and trigonal pyramidal, 100% of the time are polar. Okay, the others are where it's tricky. You just have to focus on, is everything on the outside the same? If so, it's nonpolar, or do I have some different elements on the outside? Then it's polar. Okay, so let's look at some examples. Now, these Lewis structures, these are the same ones that in the Vesper video, I went through and did the shapes, the parent structures and shapes and bond angles. And that can be helpful, you know, if you want to go through that stuff first before you figure out polarity. But basically, we'll just look at, we've got a central atom. Let's see what's attached to it. So like this carbon, and it's got two things attached, right? There's no lone pairs. So we don't have an easy way out, but you have two things attached. You have this linear structure, and one thing is a hydrogen, one is a nitrogen. So you have two different things attached. So that must be polar, okay? Because the dipole from the hydrogen and the dipole from the nitrogen are not going to be equivalent, so they can't cancel. Then we have our BH3, and so the BH3, the boron, it's got three attachments, and they're all the same. We have H and H and H. We have no lone pairs, okay? And everything attached is the same, so that must be nonpolar. Okay, so the way it's drawn, it may appear that, well, that's not symmetric because you've got one hydrogen going up and nothing going down. Well, that's because we're looking at a Lewis structure. The actual shape is trigonal planar, so they are evenly spaced out. Okay, now let's look at this SO2. In the SO2, we look at the sulfur and look at what's attached to it. So we have an oxygen, and we have a lone pair, okay? And since there is a lone pair on that central atom, for any octet structure, if there's a lone pair on the central atom, it has to be polar. You don't even have to think anymore about it. Okay, next one, let's do this PF3. Okay, so we got the PF3 on this phosphorus. We've got a fluorine, a fluorine, a fluorine, and then a lone pair. So again, we have a lone pair on that central atom. It's got to be polar. Okay. If you were dealing with exceptions and larger shapes, that's not always true, but for octet structures, it is. Okay, let's do this ammonia next, the NH4 plus. So the nitrogen has a hydrogen, a hydrogen, a hydrogen, and a hydrogen. Okay, 4 of the same thing attached and no lone pairs. So that has to be nonpolar because the dipoles from each of those hydrogens are equivalent and they're evenly spaced out at 109.5 degree angles. So overall, they will cancel and it will be nonpolar. Now the Br3 plus. The bromine has a bromine attached, another bromine attached, a lone pair, and a lone pair. So again, we have a central atom that has lone pairs on it, so it's got to be polar. Now it doesn't matter. I know it looks like you've got a lone pair on top, a lone pair on bottom, so they're completely opposite. It should cancel, but they're not completely opposite because three-dimensionally, that stuff's arranged in a tetrahedral structure. So those lone pairs are actually only 109.5 degrees from one another, not 180. Okay, and so that makes it to where kind of one end you have a bunch of negative stuff, and the other end you have these atoms. And so it's polar. And then this last one, we've got the carbonate ion. So looking at the carbon, you've got an oxygen, an oxygen, an oxygen. So 3 things attached, they're all the same element. And so that's going to be non-polar. Now I know sometimes something like this will confuse people because you have a double bond and 2 singles. And so they want to think, well, that's not completely symmetric. Even though it's trigonal planar, you've got 1 double bond. But this actually has resonance structures where the double bond can be in those other 2 locations as well. So the true structure doesn't have 2 single bonds and a double. It's some average of that. And so it actually is all the same. And so it's non-polar. Okay, so that's all the examples I'm going to go through. That should get you started. And you can always look into some more examples or ask some questions.